Right now, every plan to send humans deeper into space assumes one thing: they come back. Mars missions build return vehicles before astronauts even launch. Lunar expeditions calculate the trip home before the trip out. The entire philosophy of crewed exploration rests on a single unspoken promise: we will bring you back. But there is a destination inside our own solar system where that promise quietly breaks apart. Uranus orbits nearly 2 billion miles from Earth. A crewed spacecraft would need over a decade just to arrive. Communication with home would take over 5 hours round trip, and the energy required to slow down, enter orbit, survive, and then reverse the entire journey would demand a spacecraft so massive that no rocket on any drawing board could build it. The first humans to reach Uranus will not come back. If this kind of journey into the terrifying edges of what humans can actually survive in space is something you want to explore, do me a huge favor and hit that like button and subscribe. It really does help the channel more than you might think, and I genuinely appreciate every single one of you who sticks around for these deep dives. Now, settle in and get yourself comfortable. Let's begin. There is a picture of the solar system that lives inside nearly every human mind. You learned it as a child. You saw it on posters in classrooms, in animations on television, in the opening pages of science textbooks. The sun sits at the center. The planets orbit outward in a neat sequence. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Each one a little farther than the last. Each one a little colder. Each one a little harder to reach. The picture implies something powerful without ever saying it directly. It implies that the solar system is a ladder, that exploration is a matter of climbing it one rung at a time, that the same species which walked on the moon in 1969, which has been planning crewed Mars missions for decades, will eventually work its way outward through the giant planets in a logical, orderly progression. First Mars, then maybe the moons of Jupiter, then perhaps Saturn, and eventually, in the fullness of time, Uranus. This mental model is clean, intuitive, and completely wrong. The problem is not that the sequence is inaccurate. The problem is what the picture hides. It hides the brutal exponential way that distance grows beyond the asteroid belt, and it hides the most dangerous assumption embedded in every version of that poster. The assumption that if we can solve the problem of getting humans to Mars and bringing them home, then Uranus is simply the same problem with a longer timeline. It is not the same problem. It is not even close to the same category of problem. Understanding why requires abandoning that diagram and confronting the terrifying reality of actual distances in the outer solar system. Start with what you know. Earth to Mars. This is the mission that dominates modern space exploration planning. NASA has spent decades studying it. SpaceX has built hardware around it. The distance between Earth and Mars varies depending on where both planets sit in their orbits, but at a favourable opposition, the gap shrinks to roughly 34 million miles. Mission planners design around these favourable windows. A crewed Mars mission using current or near-future propulsion would take approximately 7 to 9 months of travel each way, with a surface stay of roughly 500 days to wait for the next return window. Round trip, you are looking at roughly 2.5 to 3 years. That is an enormous commitment by any human standard. It is longer than most military deployments. It is longer than many graduate school programs. But it is a time frame that human beings can psychologically and physically endure, and it is a time frame that engineers can design life support systems to sustain. Now move outward. Skip Jupiter entirely for a moment. Skip Saturn. Go directly to Uranus, the 7th planet from the Sun, the first of the ice giants, the planet that most people think of, if they think of it at all, as a pale blue-green dot sitting somewhere in the vague darkness beyond Saturn's rings. Uranus orbits the Sun at an average distance of roughly 1.8 billion miles. Let that number settle. 1.8 billion miles. Earth sits 93 million miles from the Sun. Mars sits 142 million miles from the Sun. Uranus sits 1.8 billion miles from the Sun. That is not twice as far as Mars. It is not 5 times as far. It is nearly 13 times farther from the Sun than Mars, and at certain points in their respective orbits, Uranus can be more than 20 times farther from Earth than Mars is. The classroom poster does not show you this. The poster compresses the outer solar system to make it fit on a sheet of paper. Jupiter, Saturn, Uranus, and Neptune get crammed into the right-hand margin, their orbits looking almost cozy. In reality, the distance between Saturn and Uranus alone is roughly 900 million miles. That single gap from one planet to its next neighbour is wider than the entire distance from the Sun to Jupiter. The outer solar system is not a continuation of the inner solar system. It is a different ocean entirely. Voyager 2 is the only human-made object that has ever visited Uranus. It launched on August 20th, 1977, from Cape Canaveral, Florida. It did not travel in a straight line. It used gravity assists from Jupiter and Saturn to accelerate, slingshotting off the gravitational fields of both planets to gain speed without burning additional fuel. Even with those gravitational boosts, even travelling faster than any crewed vehicle has ever moved, Voyager 2 took 8 years and 5 months to reach Uranus. It arrived on January 24th, 1986. It flew past the planet at a relative velocity of tens of thousands of miles per hour, took thousands of photographs, measured magnetic fields and atmospheric composition, discovered 10 new moons and 2 new rings, and then kept going. It did not slow down, it did not enter orbit, it did not stop, because stopping at Uranus was never part of the plan. Voyager 2 was designed as a flyby, and even that flyby, that brief cosmic glance, required nearly a decade of travel. Now consider what a crewed mission would actually require. A flyby is not exploration. You cannot study a planet in meaningful depth by screaming past it at tens of thousands of miles per hour. To do real science, to justify the staggering cost and risk of sending human beings instead of robots, a crew would need to enter orbit around Uranus or one of its moons. And entering orbit changes the mission equation so fundamentally that it might as well be a different endeavour entirely. Here is why. When Voyager 2 reached Uranus, it did not need to slow down because it was not staying. But a crewed vessel that intends to enter orbit must shed an enormous amount of velocity. The spacecraft arrives at Uranus carrying all the kinetic energy accumulated during years of travel and gravitational assists. To be captured into a stable orbit, it must fire its engines in the opposite direction of travel for a sustained burn, decelerating enough for Uranus's gravity to capture it. This maneuver is called orbit insertion, and it requires a terrifying amount of propellant. The amount of velocity change needed for orbit insertion is measured in a value called delta V. For a Uranus orbit insertion, depending on the trajectory and the target orbit, the required delta V can range from 1 to several kilometers per second. That might sound modest in the abstract, but in practical terms, it means the spacecraft must carry enormous quantities of fuel specifically for this single maneuver. And in spaceflight, fuel has mass. Mass requires more fuel to accelerate. More fuel adds more mass. This is the tyranny of the rocket equation. And it is the reason why deep space mission design is dominated not by what you want to do, but by how much propellant you can afford to carry. For a robotic probe, this is a serious engineering challenge, but a manageable one. The proposed Uranus orbiter and probe, which the Planetary Science Decadal Survey ranked as NASA's highest priority flagship mission in 2022, is designed with a cruise time of approximately 13 years and a spacecraft dry mass of several hundred kilograms. It would use a Falcon Heavy rocket and a Jupiter gravity assist to reach Uranus by the mid-2040s. Even this relatively lightweight robotic mission pushes current launch vehicle capabilities. The probe would carry no food, no water, no breathable air. It would not need to slow its heart rate during a solar particle event or treat a broken bone during coast phase. Its instruments would not suffer from loneliness. Its cameras would not need 8 hours of sleep. It would arrive at Uranus after 13 years of silent, patient coasting, enter orbit through a carefully calculated engine burn, and begin its 4.5-year science mission without ever once requiring a conversation with another consciousness aboard the vehicle. The total spacecraft mass for this robotic mission would be roughly 1,000 kilograms. 1,000 kilograms to reach Uranus, enter orbit, deploy an atmospheric probe, survey 5 major moons, study the ring system, characterize the magnetosphere, and transmit years of data back to Earth. That is the mass of a small car. Now imagine the mass required to keep 4 to 6 human beings alive, healthy, sane, and scientifically productive for the same journey, with the added requirement that they must eventually come home. Now multiply the mass by a factor that accounts for a pressurized crew cabin, life support systems, food, water, oxygen recyclers, radiation shielding, medical supplies, exercise equipment, backup systems for every critical component, and the fuel needed to decelerate all of that mass into Uranus orbit. Then add the fuel needed to eventually leave Uranus orbit and return to Earth. Then add the fuel needed to carry all of that return fuel to Uranus in the first place. The numbers spiral upwards so aggressively that no launch vehicle currently in existence or seriously planned can deliver the required mass to a trans-Uranian trajectory. This is where the Mars comparison becomes lethal to the imagination. Every credible Mars mission architecture ever designed is built around one unshakable principle: the crew comes home. The return is not an afterthought, it is the foundation. NASA's Mars Design Reference Architecture specifies that the return vehicle and its propellant are pre-positioned in Mars orbit before the crew even launches from Earth. The crew arrives knowing that their ride home is already waiting. The return trip uses Mars's relatively thin atmosphere for aerobraking, reducing the amount of fuel needed. The entire mission is designed so that at every stage, from launch to landing to surface operations to ascent to trans-Earth injection, the next step homeward is already engineered, tested, and verified. Uranus offers none of this. There is no atmosphere suitable for aerobraking, a crewed vehicle on approach. The planet possesses no accessible solid terrain where a crew could land or manufacture return propellant. There are no in-situ resources that current or near-future technology could exploit to manufacture return propellant. Every gram of fuel the crew needs to get home must be launched from Earth at the very beginning of the mission, carried across 1.8 billion miles of space, decelerated into Uranus orbit, stored for the duration of orbital operations, and then burned to escape Uranus's gravity well and begin the decade-long journey back. The logistical chain is not just longer than a Mars mission, it is qualitatively different. The Mars return is engineered. The Uranus return is, at present, borderline hypothetical. And that word, hypothetical, reveals the true fracture between these two mission classes. When engineers talk about sending humans to Mars, they argue about timelines, budgets, and specific technologies. They argue about whether to use chemical propulsion or nuclear thermal propulsion, whether to send 4 crew members or 6, whether to stay for 30 days or 500. These are arguments about optimization. The fundamental feasibility is accepted. When engineers talk about sending humans to Uranus, the conversation does not even reach those details. It stalls at a more basic question. Can we physically build a spacecraft large enough, carry enough fuel, sustain a crew long enough, and guarantee a return trajectory reliable enough to make a round trip survivable? The honest answer in 2026 is that we cannot. Not with any technology that exists or is likely to exist within the next several decades. The travel time alone should stop most dreamers in their tracks. A crewed mission to Uranus using nuclear thermal propulsion, the most promising near-future technology for deep space crewed travel, would require somewhere between 12 and 17 years of one-way travel time, depending on the trajectory, the gravity assists available, and the mass of the vehicle. Let those numbers land. 12 to 17 years, not months, years. A crew that departed Earth in their mid-30s would arrive at Uranus approaching 50. They would have spent the entirety of their 40s inside a spacecraft, watching their children grow from toddlers to teenagers through video messages that take hours to deliver and hours more to receive a response. And they would have arrived not at a destination that welcomes them, but at a pale, featureless, frozen giant hanging in permanent darkness, offering nothing except the scientific data they came to collect and the realization that the return journey is just as long as the one they just endured. Compare this to every human spaceflight record ever set. The longest continuous stay in space by a single human being is Valery Polyakov's 437 days aboard the Mir space station, completed in 1995. That is roughly 1 year and 2 months. The longest total time spent in space by any human across multiple missions belongs to Oleg Kononenko, who surpassed 1,100 days in 2024. That is roughly 3 years. A one-way trip to Uranus would require at least 12 years. A round trip would consume 25 to 35 years. These durations exceed the entire accumulated spaceflight experience of the most seasoned astronaut who has ever lived by a factor of 10 or more. There is no medical data on what happens to the human body after 12 continuous years in space. There is no psychological data on what happens to a crew confined together in a sealed environment for that duration. There is no engineering data on whether life support systems, water recyclers, air scrubbers, power generators, or radiation shields can function reliably for 2 or 3 decades without Earth-based maintenance. We do not know these things because no one has ever tried them, and no one has ever tried them, because the question has never been relevant until you start talking about destinations as remote as Uranus. And yet the quiet assumption persists. The assumption that Uranus is simply the next planet out, that it belongs on the same list as Mars and Jupiter, that the species which landed 12 human beings on the Moon will, given enough time and funding, walk its way outward through the solar system the way settlers once walked westward across a continent. The analogy is seductive and misleading. Settlers moving westward faced escalating hardship, but the nature of the challenge remained fundamentally consistent. More distance meant more desert, more mountains, more rivers to cross, but the human body could still function. Food could still be gathered. Water could still be found. The air was still breathable. The ground was still solid. The solar system does not scale this way. Moving from Mars to Uranus is not like crossing a wider desert. It is like stepping off the edge of the continental shelf into an oceanic trench. The nature of the challenge changes. Distance stops being an inconvenience and becomes a structural impossibility. The gap between what human beings need to survive and what the destination offers does not widen gradually. It collapses suddenly and completely. Consider just one variable to glimpse the scale of the difference. Sunlight. At Mars, the sun still delivers roughly 43% of the solar energy that reaches Earth. Spacecraft there use solar panels routinely. At Uranus, the sun delivers roughly 1/400th of Earth's solar energy. Solar power is effectively useless. A crewed mission would depend entirely on nuclear power systems whose fuel must be carried from Earth and whose operational lifespan must stretch across decades without maintenance. The full weight of that energy problem will become clear when we examine what awaits the crew upon arrival. But energy is only one variable among many. Food is another. Water recycling is another. Air composition is another. Radiation shielding is another. Psychological endurance is another. Mechanical reliability across decades of continuous operation is another. Each of these is a serious engineering challenge on a 3-year Mars mission. On a 25-year Uranus round trip, each one becomes a potential mission-ending failure mode. The most important thing to understand is not any individual fact or figure. It is the pattern. The pattern that emerges when you stop thinking of the solar system as a ladder and start thinking of it as a series of concentric walls, each one taller and thicker than the last. Mars sits behind a wall that is tall but climbable, with technology that either already exists or is actively under development. Jupiter sits behind a wall that is much taller, probably requiring nuclear propulsion and advanced radiation shielding that do not yet exist in operational form. Saturn sits behind a higher wall still, and Uranus sits behind a wall so high that from the ground you cannot see the top. The illusion of the next step is the belief that every wall is the same wall, just taller, that the skills you learn climbing the Mars wall will transfer directly to the Uranus wall, that the same basic mission architecture, launch, cruise, arrive, operate, and return, will work at every distance if you simply scale it up. It will not. And the reason it will not has nothing to do with ambition, funding, or political will. It has to do with physics, with the rocket equation, with the speed of light, with the biological limits of the human body, with the thermodynamic reality of operating a crude habitat in deep space for durations that exceed anything our species has ever attempted. Uranus is not the next step on the ladder. It is the step where the ladder ends and something else begins. Something that looks less like exploration and more like exile. Something that forces a question no space agency has ever had to answer honestly. What happens when the destination is reachable, but the return is not? That question will sharpen into focus as we examine exactly what happens when 2.5 hours of communication delay meets a crew that can no longer rely on Earth for anything at all. On March 14th, 2016, the European Space Agency's ExoMars Trace Gas Orbiter launched from Baikonur Cosmodrome in Kazakhstan, carrying a small landing demonstrator called Schiaparelli. 7 months later, on October 19th, Schiaparelli separated from the orbiter and began its descent toward the Martian surface. Everything proceeded according to plan until it did not. Approximately 50 seconds before touchdown, the lander's inertial measurement unit generated a saturation error. The onboard computer misinterpreted the data, concluded it was at or below ground level, jettisoned its parachute early, and fired its braking thrusters for only 3 seconds instead of the planned 30. Schiaparelli was still 2.3 miles above the surface. It fell for the remaining distance in free fall and slammed into Mars at over 300 kilometers per hour, shattering on impact. The entire failure, from the first erroneous sensor reading to the final crash, lasted less than 1 minute. Here is the detail that matters for our story. When Schiaparelli hit the ground, the signal confirming its destruction had not yet reached Earth. The one-way light delay between Mars and Earth on that day was approximately 9 minutes and 46 seconds. Engineers at the European Space Operations Center in Darmstadt, Germany, were still watching telemetry from nearly 10 minutes in the past. By the time they realized something had gone wrong, the lander had already been debris for the better part of a quarter hour, 9 minutes and 46 seconds. That was the communication delay that made it impossible to intervene, impossible to correct, impossible to send a single command that might have saved the mission. And Mars, relative to the outer solar system, is practically next door. Now multiply that delay by a factor of 15. At Uranus, the one-way light travel time from Earth varies depending on the orbital positions of both planets. But at an average separation of roughly 1.8 billion miles, a radio signal or laser pulse traveling at the speed of light requires approximately 2 hours and 40 minutes to make the one-way journey. That means a round-trip communication exchange. The time between sending a question and receiving an answer takes a minimum of 5 hours and 20 minutes. Under less favourable orbital geometries, when Earth and Uranus sit on opposite sides of the Sun, that round-trip delay can stretch beyond 5.5 hours. Let the operational reality of that number settle into your thinking. A crew member aboard a spacecraft in Uranus orbit notices an anomalous reading on a life support pressure gauge. They compose a message describing the anomaly, attach relevant telemetry data, and transmit it to Mission Control in Houston. Then they wait. 2 hours and 40 minutes later, a technician at the Johnson Space Center receives the message, pulls up the telemetry, consults with systems engineers, drafts a response with diagnostic instructions, and transmits it back. 2 hours and 40 minutes after that, the crew member receives the reply. The total elapsed time from initial observation to receiving expert guidance is now over 5 hours. If the anomaly was the first sign of an atmospheric leak, the crew would either have solved the problem themselves or suffocated long before Houston's advice arrived. This is not a theoretical concern. This is the foundational operational reality of any mission beyond Saturn. At Mars, the communication delay is inconvenient but manageable. Human crews could still maintain something resembling a conversation with Earth, asking a question at breakfast and receiving an answer before lunch. The delay imposes a rhythm, but it does not sever the connection. Mission Control can still participate in decision-making within the same day. At Uranus, that connection does not just weaken, it functionally ceases to exist in any operational sense. A crew at Uranus cannot consult Earth about an emergency. They cannot request real-time guidance during a critical maneuver. They cannot receive updated trajectory calculations during a time-sensitive orbital adjustment. They cannot even have a morale-boosting conversation with a psychologist without treating it as a series of 5-hour delayed monologues. The communication link becomes what engineers call store and forward. Messages sent, messages received, but no interaction, no dialogue, no real-time human connection. The crew is alone in every way that matters. The medical consequences of this isolation deserve their own reckoning because they reveal something that abstract discussions of communication delay cannot. They reveal what the delay costs in flesh. On the International Space Station, medical emergencies are rare but not unprecedented. Astronauts have experienced dental abscesses, allergic reactions, minor lacerations, urinary tract infections, and cardiac arrhythmias. In each case, the crew member consulted with flight surgeons on the ground in near real time. Telemetry from onboard medical monitors was transmitted to the Johnson Space Center, where physicians reviewed the data and provided diagnostic guidance within minutes. When Canadian astronaut Chris Hadfield experienced temporary blindness in both eyes during a spacewalk when anti-fog solution from inside his helmet leaked into his eyes, Mission Control talked him through the response step by step. When astronaut Serena Aunion-Chancellor developed a deep vein thrombosis, a potentially life-threatening blood clot in her jugular vein, during her mission aboard the station in 2018, a team of radiologists and vascular specialists on the ground reviewed her ultrasound images within hours and guided her through a months-long anticoagulant treatment protocol. The clot was managed successfully. She returned to Earth alive. At Uranus, Serena Aunion-Chancellor would very likely be dead. Not because the clot itself was untreatable, not because the ultrasound equipment would be absent from the spacecraft, but because the diagnosis required specialist interpretation that no generalist crew member could provide with confidence, and the treatment protocol required ongoing consultation with vascular medicine experts who could adjust dosages based on follow-up imaging. Each consultation cycle, sending images to Earth, waiting for analysis, receiving updated instructions, would consume over 5 hours. A deep vein thrombosis can dislodge and become a pulmonary embolism, a clot in the lungs, within minutes. The window between a manageable condition and a fatal one is measured in hours, not days. A crew at Uranus would need to diagnose, treat, and manage the condition entirely on their own, using medical training that, however extensive, cannot replicate the depth of a vascular surgery fellowship. And blood clots are not the most frightening scenario. Consider appendicitis. On Earth, a ruptured appendix is a surgical emergency that kills within days if untreated. The treatment is an appendectomy, a routine operation in a hospital, but an extraordinarily dangerous procedure in a spacecraft. Some Mars mission planners have proposed prophylactic appendectomies for crew members before departure, removing the appendix preemptively to eliminate the risk. This is a reasonable precaution for a 3-year mission. For a 25-year Uranus mission, the list of organs and conditions that might require surgical intervention over a quarter-century of life is far too long for prophylactic removal to address. Gallstones, kidney stones large enough to obstruct the ureter, hernias, intestinal obstructions, bone fractures requiring surgical repair, dental emergencies requiring extraction, or root canal, under anesthesia, tumors. The radiation environment of deep space significantly elevates the crew's cumulative cancer risk over the mission duration. If a crew member develops a malignant tumor in year 9 of the outbound cruise, the treatment options available aboard the spacecraft would be limited to whatever surgical capability and pharmaceutical stockpile was loaded before departure. There would be no oncologist, no radiation therapy equipment, no chemotherapy infusion center, no pathology lab to analyze biopsied tissue. The crew member and their shipmates would face an agonizing decision: attempt a surgical resection with improvised tools and non-specialist hands, administer whatever anti-cancer drugs happen to be aboard, and hope the formulation matches the cancer type, or accept the diagnosis as terminal and manage the crew member's decline over months or years while the rest of the crew continues the mission. Every one of these scenarios has been studied in the context of Mars missions. NASA's Human Research Program maintains an extensive evidence base on medical risks for long-duration spaceflight, and the Mars Design Reference Architecture includes detailed medical kit specifications, crew medical training requirements, and contingency protocols for a range of emergency scenarios. But these plans are designed for missions lasting 3 years, not 25. The probability of a crew member experiencing a serious medical event during a 3-year mission is calculated in the low single-digit percentages. Over 25 years, the cumulative probability that at least one crew member will face a life-threatening medical condition that would be routine to treat on Earth, but nearly impossible to manage in a deep space habitat, approaches something closer to certainty. The pharmaceutical stockpile presents its own degradation problem. Medications have shelf lives. Most oral drugs begin to lose potency after 2 to 5 years, even under ideal storage conditions. Injectable medications degrade faster. Antibiotics, analgesics, cardiac drugs, anti-seizure medications, epinephrine, insulin, all have finite stability windows that fall far short of a 25-year mission duration. Some researchers have proposed onboard pharmaceutical manufacturing, using raw chemical precursors and automated compounding equipment to produce medications on demand. This technology is in its infancy and has never been tested in spaceflight. A crew relying on it would be trusting their lives to a prototype drug factory operating in a radiation-soaked, microgravity environment for decades, without maintenance support from Earth. The medical autonomy problem crystallizes the compounding cost of remoteness more viscerally than any engineering calculation. Delta V budgets and mass ratios are abstractions. The image of a crew member bleeding internally while their shipmates attempt surgery by the light of a headlamp, guided by a medical textbook loaded onto a tablet, with the nearest hospital 2 billion miles and 15 years away, is not an abstraction. It is the human reality of what 5 hours of communication delay actually means when the emergency is not a sensor glitch or a software error, but a body that is failing. This isolation transforms the crew from passengers and operators into something unprecedented in the history of human spaceflight. They must become their own mission control. Every function that has traditionally been distributed across thousands of ground personnel, trajectory analysis, systems monitoring, failure diagnosis, medical evaluation, science planning, schedule management, resource allocation, must be performed by the crew themselves, in real time, with no external verification and no safety net. The psychological literature on long-duration spaceflight isolation refers to this condition as Earth-independent operations, and it has been studied extensively in the context of Mars missions. But the studies always assume a delay measured in minutes, not hours. They assume that while real-time conversation is impossible, same-day problem-solving is not. They assume that in a genuine emergency, a crew could transmit a distress signal and receive meaningful help within an hour. At Uranus, none of these assumptions hold. A crew facing a genuine emergency, whether a fire, a decompression, a medical crisis, a navigation error, or a critical systems failure must resolve it entirely on their own or die. There is no cavalry. There is no abort option. There is no emergency return trajectory that gets them home in time for a rescue. The nearest human beings are 1.8 billion miles away, separated by a communication gap wider than any ocean, any desert, any distance that any human crew has ever faced. And communication delay is only the first compounding factor. It multiplies every other challenge the mission faces, transforming manageable problems into existential ones. Consider life support. On the International Space Station, which orbits approximately 250 miles above Earth's surface, life support systems are maintained by a combination of onboard crew and continuous ground support. When a carbon dioxide scrubber fails, replacement parts can be delivered on the next resupply mission, typically within weeks or months. When a water recycler malfunctions, engineers on the ground analyze telemetry, identify the fault, and uplink repair procedures. The station is resupplied by cargo spacecraft from multiple nations several times per year, bringing food, water, spare parts, experiments, and crew comfort items. On a Mars mission, resupply becomes impossible during the transit phases, but the total mission duration of roughly 3 years means that engineers can pre-position enough consumables and spare parts to cover the entire mission with reasonable margins. If a critical system fails, the crew can attempt repairs using onboard spares, and if the repair fails, the mission timeline is short enough that degraded operations can sustain the crew until they return home. At Uranus, the mission duration obliterates both of these safety models. A round-trip mission would span roughly a quarter century at minimum and could stretch past 3 decades, depending on propulsion technology, trajectory design, and the duration of orbital operations at Uranus. During that entire span, the crew receives 0 resupply. Every calorie of food, every litre of water, every canister of breathable atmosphere, every replacement filter, every circuit board, every bolt and washer and tube of adhesive must be loaded onto the spacecraft before it leaves Earth orbit. There is no second shipment. There is no emergency delivery. If a water recycler fails in year 7 of the outbound cruise and the crew cannot repair it with onboard materials, they will die of dehydration billions of miles from home with no possibility of rescue. The mass implications of this requirement are staggering. NASA's Mars mission architecture studies suggest that a crew of 4 requires on the order of 15,000 to 30,000 kilograms of consumables, spare parts, and life support equipment for a 3-year mission. Scale even the lower end of that range linearly to a multi-decade Uranus mission, and you reach hundreds of thousands of kilograms of consumables alone before accounting for crew habitat mass, propulsion systems, scientific instruments, or fuel. And linear scaling is optimistic because longer missions require exponentially more redundancy. On a 3-year mission, you might carry 2 backup water recyclers. On a 25-year mission, you need backups for the backups and repair kits for the backups of the backups. Because the probability of multiple sequential failures over that time frame approaches certainty, every additional kilogram of mass that must reach Uranus orbit imposes a cascading cost on the propulsion system. This is where the rocket equation becomes not just a constraint but a wall. The Tsiolkovsky rocket equation describes the relationship between a spacecraft's velocity change, the efficiency of its engine, and the ratio of its initial mass, fully fueled, to its final mass, after burning all propellant. The relationship is logarithmic, which means that adding a small amount of payload mass requires a disproportionately large increase in fuel mass. Double the payload does not mean double the fuel. It can mean 4 times the fuel, or 8 times, depending on the delta-V requirements. For a Uranus mission, the total delta-V budget is enormous. The spacecraft must accelerate out of Earth orbit, execute orbit insertion at Uranus, conduct orbital maneuvers during the science phase, escape Uranus orbit, and decelerate into Earth orbit upon return. The propellant for later phases must be carried through all earlier phases, adding mass that requires even more propellant to accelerate. The return fuel becomes the single largest mass driver of the entire mission. This is the insight that separates Uranus from Mars in the most fundamental way possible. On a Mars mission, the return fuel is a manageable fraction of the total mission mass. Engineers can even manufacture some of the return propellant on Mars itself using in-situ resource utilization, converting Martian carbon dioxide and water ice into methane and liquid oxygen. This dramatically reduces the amount of return fuel that must be launched from Earth. On a Uranus mission, there is no in-situ resource utilization. Uranus has no accessible solid surface. Its moons are small, icy bodies with no confirmed deposits of useful propellant precursors. Every kilogram of return fuel must be launched from Earth, accelerated to trans-Uranian velocity, carried for over a decade through deep space, decelerated into Uranus orbit, stored throughout the operational phase, and then burned to escape the Uranian system. The tyranny of the rocket equation turns this return fuel into the dominant mass element of the mission. In some preliminary analyses, the return propellant accounts for more than 70% of the spacecraft's initial mass in Earth orbit. This is not an engineering inconvenience. It is a structural impossibility with current technology. The spacecraft required to execute a crewed Uranus round trip would need to be assembled in orbit from multiple launches, each one costing billions of dollars, with in-space assembly techniques that have never been demonstrated at this scale. The total mass in low Earth orbit required to support such a mission would likely exceed 1 million kilograms, roughly 5 times the mass of the International Space Station, which itself required over 30 missions and more than a decade to assemble. And unlike the space station, which was built in a comfortable low Earth orbit where resupply and crew rotation were straightforward, a Uranus mission vehicle must be fully assembled, fully tested, and fully provisioned before departure. Once it leaves Earth orbit, there are no corrections, no additions, no do-overs. Now layer the propulsion burden on top of the communication delay and the life support duration. Each problem feeds the others. The communication delay means the crew cannot receive real-time engineering support, which means the spacecraft must carry more redundant systems, which adds mass, which requires more fuel, which adds more mass. The extended mission duration means more consumables, which adds mass, which requires more fuel. The fuel for the return trip must survive decades of storage in deep space, enduring thermal cycling, radiation exposure, and micrometeorite impacts, which requires additional shielding and containment systems, which adds mass. Every solution to one problem creates a new mass penalty that worsens every other problem. This compounding spiral is why experienced mission designers describe Uranus not as a harder destination, but as a different class of destination. The word they use most often in technical literature is prohibitive, not impossible in the absolute physics sense, because nothing about a Uranus mission violates the laws of physics, but prohibitive in the practical engineering sense, meaning that the resources required exceed anything that foreseeable technology, funding, or institutional commitment can provide. Radiation adds yet another compounding layer. In low Earth orbit, the International Space Station sits within Earth's magnetosphere, which deflects most of the high-energy particles streaming from the Sun and from galactic sources. Astronauts aboard the station still receive elevated radiation doses compared to people on Earth's surface, but the exposure is manageable for missions lasting a year or two. On a Mars mission, the crew spends approximately 7 to 9 months in interplanetary space each way, exposed to galactic cosmic rays and the risk of solar particle events. This is a serious concern, and Mars mission planners devote significant effort to radiation shielding design. But the total transit time through unshielded space is roughly 14 to 18 months, plus whatever time the crew spends on the Martian surface, where the planet itself provides partial shielding from below. On a Uranus mission, the crew spends the overwhelming majority of their mission in interplanetary space with no planetary body providing any shielding at all. 12 to 17 years of outbound travel, a period of orbital operations at Uranus, and 12 to 17 years of return travel. That is 25 to 35 years of continuous exposure to galactic cosmic rays, which are high-energy particles, primarily protons and heavier nuclei, that no practical amount of shielding can fully stop. Galactic cosmic rays are so energetic that they penetrate several meters of solid material, even inside a heavily shielded spacecraft. The crew would accumulate radiation doses far exceeding any limits currently established by space agencies. NASA's current career radiation exposure limit for astronauts is calibrated to ensure that an individual's risk of exposure-induced death from cancer does not exceed a certain threshold. As of 2022, NASA standardized this to a single career dose limit of 600 millisieverts for all astronauts, regardless of age or sex. On a Uranus round trip, depending on shielding effectiveness and solar activity, the crew could accumulate total doses measured in the thousands of millisieverts, potentially exceeding the career limit by a factor of 10 or more based on interplanetary radiation measurements from the Mars Science Laboratory. The biological consequences of sustained exposure at that level are not precisely known because no human has ever experienced it, but extrapolations from radiation biology suggest significantly elevated lifetime cancer risk, potential central nervous system effects including cognitive degradation, and possible cardiovascular damage. The radiation problem has no clean solution. You can add more shielding, but shielding adds mass, which requires more fuel, which adds more mass. You can design the spacecraft with a heavily shielded storm shelter for use during solar particle events, but galactic cosmic rays cannot be sheltered against in the same way because they come from all directions continuously. Some researchers have proposed using magnetic fields to deflect charged particles, but generating a magnetic shield strong enough to protect a crude volume in deep space requires enormous power and superconducting magnets whose feasibility in this application remains entirely unproven. Every proposed mitigation adds complexity, mass, power demands, and failure modes. And then there is the human mind. Psychological research on long-duration isolation is extensive but limited in scope. Antarctic winter-over cruise, submarine deployments, space station expeditions, and ground-based isolation studies like Mars 500 and Sirius have provided valuable data on how humans respond to confinement, monotony, interpersonal conflict, sleep disruption, and separation from family. But even the longest of these studies lasted only 520 days, and the participants knew throughout that they could be evacuated in an emergency. They knew that Earth was reachable. They knew that the experiment had an end date that fell within a psychologically manageable time frame. A Uranus crew would face isolation of a categorically different nature. Not 500 days, not even 1,000 days, over 9,000 days, outbound alone, with no possibility of evacuation, with the knowledge that if a crew member suffers a psychotic break, a severe depressive episode, or a violent interpersonal conflict, there is no way to remove them from the group, no way to bring in a replacement, no way to adjust the social dynamics of a tiny sealed community hurtling through the void at tens of thousands of miles per hour. The crew must function as a unit for decades. They must maintain professional relationships, manage conflicts, sustain motivation, and preserve cognitive function through years of monotony punctuated by rare intervals of intense activity. No human group has ever been tested under these conditions. No psychological model can predict with confidence whether it is even possible. Studies of isolated Antarctic crews have documented phenomena including insomnia, irritability, cognitive slowing, depression, hostility, and social withdrawal, and these appear in groups that know they will be relieved within 12 months. In Mars 500, which confined 6 crew members in a simulated spacecraft for 520 days, researchers observed significant disruptions to sleep-wake cycles, reduced activity levels, and psychological withdrawal among crew members during the middle portion of the mission. The psychological literature refers to this as the third quarter effect, a predictable decline in morale and performance that occurs roughly 3/4 of the way through any confined mission, when the novelty has worn off and the end is not yet visible. On a Uranus mission, The third quarter effect would arrive not after a few months, but after years. The crew would hit this psychological trough somewhere around year 8 or 9 of the outbound cruise, still years away from Uranus, already years away from Earth, with nothing visible outside the windows except the same unchanging star field they have been staring at since departure. The nearest planet would be a faint dot. Earth would be a pale blue pixel indistinguishable from hundreds of other stars. The sun would be a slightly brighter point of light, no longer capable of warming skin or illuminating a room. The crew would exist in a sensory environment so impoverished that it defies comparison to any human experience in history, and there would be no rescue, no abort, no option to turn back early if someone breaks down, no option to call for help if the group dynamic collapses. The crew is committed from the moment they leave Earth orbit. The trajectory is fixed, the propellant is allocated, the consumables are finite. There is no shortcut home, there is no emergency exit. There is only the mission, stretching forward through years of emptiness toward a destination that offers no comfort and no relief, followed by more years of emptiness on the return. Every element of the mission reinforces every other element in a feedback loop of compounding difficulty. The distance creates the communication delay. The delay creates the autonomy requirement. The autonomy requirement demands more onboard systems and redundancy. More systems mean more mass. More mass demands more fuel. More fuel adds more mass. The extended mission duration demands more life support consumables, which add more mass. The radiation exposure increases with duration, requiring more shielding, which adds more mass. The psychological strain increases with duration and isolation, demanding more crew support systems, which add more mass. Every solution feeds the problem it was meant to solve. This is the compounding cost of remoteness. It is not that any single challenge of a Uranus mission is unsolvable in isolation. Communication delay can be managed with autonomous systems. Life support can be extended with closed-loop recycling. Radiation can be partially mitigated with shielding. Propulsion can theoretically be scaled up with nuclear systems. Psychological strain can be partially addressed with crew selection and support protocols. But when you stack every one of these challenges on top of every other one, and you apply them all simultaneously over a duration of 25 to 35 years with no resupply, no rescue, and no margin for error, the total burden exceeds anything that current or near-future engineering can carry. The Mars mission is hard. The Uranus mission is not harder. It is a different thing entirely. It is what happens when distance stops being a number and starts being a force that multiplies every vulnerability, amplifies every risk, and strips away every safety net that human spaceflight has always relied upon. And the destination itself, the pale frozen giant waiting at the end of that decade-long journey, offers nothing to ease the burden. What arrives to greet the crew at Uranus is not a new world full of possibilities. It is a world that actively refuses human presence. That is what comes next. Every destination humanity has ever explored, from the bottom of the ocean to the surface of the moon, has offered something upon arrival. Some resource, some foothold, some physical feature that a human crew could use, study from close range, or build upon. The deep ocean floor offered mineral deposits and bizarre ecosystems clustered around hydrothermal vents. Antarctica offered solid ground, breathable air at the surface, and ice that could be melted for water. The moon offered a rocky surface to stand on, regolith that could be studied, and a gravity well shallow enough that returning home required a single engine burn lasting 7 minutes. Even Mars, the most ambitious crewed destination currently under serious planning, offers a solid surface, a thin but real atmosphere that can be used for aerobraking and potentially for manufacturing propellant. Water ice buried beneath the regolith, a day-night cycle almost identical to Earth's, and a gravitational pull just strong enough to keep human bones from deteriorating as rapidly as they would in microgravity. Uranus offers none of this. Not one element. The seventh planet from the Sun is not merely inhospitable. It is fundamentally incompatible with human presence in a way that no previously considered crewed destination has ever been. Begin with the most basic question any explorer asks upon arrival. Where do we land? On the Moon, you land on the surface. On Mars, you land on the surface. On the moons of Jupiter, if a crewed mission ever reaches them, you land on their surfaces. Landing gives you a fixed reference point, a base, a place to stand while you do your work. At Uranus, there is no surface. The planet is classified as an ice giant, but the word ice is misleading. It is a massive sphere of gas and supercritical fluid, roughly 4 times the diameter of Earth, with a deep interior of water, methane, and ammonia compressed to pressures so extreme that the materials behave like hot, dense liquid, rather than anything resembling familiar ice. There is no boundary between atmosphere and surface. No solid ground exists at any depth that a spacecraft could reach. The atmosphere simply grows denser and hotter as you descend, transitioning smoothly from thin gas to crushing fluid. At the depth where pressures reach the levels found at the bottom of Earth's deepest ocean trenches, you are still thousands of kilometers from anything that might be called a core. And that core, if it exists in any distinct form, is a region of rock and exotic ices compressed to temperatures exceeding 4,000 degrees Celsius, under pressures millions of times greater than Earth's atmospheric pressure at sea level. A spacecraft descending into Uranus would not land. It would be progressively crushed and dissolved. The atmospheric probe proposed for the robotic Uranus orbiter and probe mission is designed to survive to a depth of roughly 1 to 5 atmospheres of pressure, transmitting data for approximately 90 minutes before the increasing heat and compression destroy it. That probe is a small, ruggedized capsule with no crew aboard. A crewed vehicle could not even attempt this descent. There is no destination at Uranus in the physical sense that the word has always carried in exploration. There is only an atmosphere that gets progressively more lethal the deeper you go, surrounding a core that would vaporize any known material long before you reached it. This means that a crewed mission to Uranus is not a landing mission. It is an orbital mission. The crew would remain aboard their spacecraft, circling the planet from a safe distance, operating instruments remotely, and deploying probes into the atmosphere below. This is scientifically valuable but operationally devastating, because it eliminates every advantage that a human crew might offer over a robotic one. The primary justification for sending humans instead of robots to any destination has always been adaptability. Humans can react to unexpected discoveries in real time. They can improvise repairs, adjust experimental protocols on the fly, and make intuitive decisions that robotic systems cannot replicate. On the lunar surface, Apollo astronauts recognized geologically significant rocks by sight and altered their collection plans accordingly. On Mars, human geologists could examine outcrops, drill cores, and make field decisions about where to look for biosignatures far more effectively than any rover. These advantages depend on physical presence. On the human being standing on the ground, touching the rocks, seeing the terrain with their own eyes. In orbit around Uranus, these advantages vanish. The crew cannot walk on the planet. They cannot collect samples by hand. They cannot examine surface features in person because there is no surface. They operate instruments from inside a sealed spacecraft, processing data on screens, commanding robotic probes via radio links that function identically whether the operator is in orbit around Uranus or sitting in a control room on Earth. The 13-year communication delay between Earth and a robotic Uranus orbiter is a genuine limitation that a local crew could overcome by providing real-time probe command. But the question becomes whether overcoming that limitation justifies sending human beings on a 25-year round trip through the most hostile environment in the solar system. The answer, in cost-benefit terms, is almost certainly no. The moons of Uranus add complexity to this picture, but do not fundamentally change it. Uranus has 27 known moons, 5 of which are large enough to be considered major satellites: Miranda, Ariel, Umbriel, Titania, and Oberon. These moons are geologically fascinating. Miranda, the smallest of the five, displays one of the most bizarre surfaces in the solar system, a fractured, jumbled landscape of intersecting ridges, deep canyons, and mismatched terrain that suggests the moon was either torn apart and reassembled by tidal forces or experienced cryovolcanic resurfacing at some point in its past. Aerial shows signs of relatively recent geological activity, with smooth plains and flow features that may indicate past eruptions of water-ammonia mixtures. Both Miranda and Ariel are considered possible ocean worlds, meaning they might harbour subsurface liquid water oceans beneath their icy crusts, maintained by tidal heating from Uranus. These are extraordinary scientific targets. But being extraordinary scientific targets does not make them viable destinations for human crews. Titania, the largest, has a surface gravity approximately 4% of Earth's. Miranda, the most geologically interesting, is only 290 miles across, with surface gravity less than 1% of Earth so weak that an astronaut standing on its surface could throw a baseball into orbit. These are tiny, icy worlds with no atmospheres, no protection from radiation, and no accessible resources that could support a human presence. Landing a crewed vehicle on one of these moons would require yet another propulsion stage, additional fuel for descent and ascent, surface habitat modules, extravehicular activity suits designed for near-vacuum conditions, and power systems capable of operating on surfaces that receive almost no sunlight. The surface temperature on the Uranian moons hovers around -200 degrees Celsius. At that temperature, metals become brittle, lubricants freeze solid, and battery chemistry degrades catastrophically. Every piece of equipment designed for surface operations would need to be engineered for thermal extremes that far exceed anything faced on the Moon or Mars. And even if a surface mission to one of Uranus's moons were technically feasible, the scientific return would not justify the incremental cost and risk. A robotic lander equipped with a drill, spectrometers, and seismometers could investigate the surface composition, search for evidence of subsurface liquid, and return data to an orbiting relay for transmission to Earth. This is precisely what the robotic Uranus orbiter and probe concept is designed to do, without the need to keep human beings alive on an airless ice ball 2 billion miles from home. Now consider energy. At Earth's distance from the Sun, every square metre of surface oriented toward the Sun receives approximately 1,361 watts of solar energy. This is enough to power modern solar panels at efficiencies of roughly 20 to 25%, generating several hundred watts per square metre. Solar energy is the backbone of most near-Earth spacecraft and plays a significant role in Mars mission concepts. At Jupiter, roughly 5 astronomical units from the Sun, solar intensity drops to about 50 watts per square metre. This is still usable, as the Juno spacecraft demonstrates, but it requires very large solar arrays. At Uranus, roughly 19 astronomical units from the Sun, solar intensity plummets to approximately 3.4 watts per square metre. This is not a reduction, it is an elimination. To generate the same electrical output as a modest rooftop solar installation on Earth, a spacecraft at Uranus would need solar panels covering an area larger than several football fields. The structural mass alone of such an array, before accounting for deployment mechanisms, pointing systems, and wiring, would add tens of thousands of kilograms to the spacecraft. Solar power is therefore not viable at Uranus for any practical purpose. The mission must rely entirely on nuclear power. The two candidate technologies are radioisotope thermoelectric generators and compact fission reactors. Radioisotope thermoelectric generators are proven technology, used on Voyager, Cassini, New Horizons, and the Mars Curiosity and Perseverance rovers. They convert heat from the natural decay of plutonium-238 into electricity. They are reliable, long-lived, and require no moving parts, but their power output is modest, typically between 110 and 300 watts of electrical power per unit at the beginning of their life, depending on the generator design, and their output decays over time due to both plutonium decay and thermocouple degradation. Real-world performance data from Mars rovers shows total power loss rates significantly exceeding simple fuel decay. After a decade, a generator may produce only 60 to 70% of its initial output. After 25 years, the remaining power could fall well below half the starting figure. A crewed spacecraft requires vastly more power than a robotic probe. Life support systems, thermal regulation, lighting, computers, communications transmitters powerful enough to send data across nearly 2 billion miles, scientific instruments, and the various pumps, fans, compressors, and motors that keep a habitat functional demand continuous electrical power on the order of tens of kilowatts minimum. To provide this from radioisotope thermoelectric generators alone would require dozens of units, each containing several kilograms of plutonium-238, a material so scarce and expensive that the United States restarted domestic production in 2015 after a gap of nearly 3 decades, and the Department of Energy's target production rate is only approximately 1.5 kilograms per year. A crewed Uranus mission requiring 50 or more kilograms of plutonium-238 would consume decades of production capacity before a single watt was generated. The alternative is compact fission reactors. NASA and the Department of Energy have developed small fission reactor concepts, including the kilopower demonstrator that produced approximately 1 kilowatt, and the more ambitious Fission Surface Power project, targeting approximately 40 kilowatts for lunar surface operations. These reactors use enriched uranium fuel and Stirling engines to convert thermal energy into electrical power. They represent a promising technology path, but as of 2026, no fission reactor has been operated in space by the United States since the Snapton-A experimental reactor in 1965, which ran for only 43 days before a voltage regulator failure shut it down. Operating a fission reactor aboard a crewed spacecraft for 25 to 35 years continuously, without the ability to perform physical maintenance, replace worn components, or refuel, is an engineering challenge without any precedent in the history of spaceflight or terrestrial nuclear operations. Reactor fuel rods degrade over time, control mechanisms wear, radiation damages reactor structural materials, cooling systems develop leaks. Every failure mode that nuclear engineers manage in terrestrial reactors through regular inspection, maintenance, and refueling must instead be prevented entirely through design robustness, because a crew 2 billion miles from Earth cannot call a nuclear maintenance team, and power is not the only resource the destination fails to provide. Water, oxygen, and food are the 3 consumables that dominate life support planning for any crewed mission. On the International Space Station, water is recycled with approximately 93% efficiency, meaning the station recovers roughly 93% of the water it uses, including water reclaimed from crew urine and atmospheric humidity. The remaining 10% is lost and must be resupplied from Earth. On a 3-year Mars mission, this loss rate is manageable. Pre-positioned supplies and slight margins cover the gap. On a 25-year Uranus mission, a 10% water loss rate compounds into a catastrophic deficit. If the crew begins with 10,000 kilograms of water, they lose 1,000 kilograms per year to inefficiency. After 10 years, half their water is gone. Before the mission is half over, they face rationing, dehydration, or death. To avoid this, the water recycling system must achieve efficiency above 99% sustained over decades without failure. No such system exists. Even the most advanced recyclers currently operational require regular maintenance, filter replacement, and occasional major component swaps using parts delivered from Earth, and they still lose several percent of total water volume per cycle. Food presents an even more intractable problem. Current space food technology relies on prepackaged meals with a shelf life of approximately 2 to 3 years. Beyond that time frame, nutritional content degrades, flavors deteriorate, and the caloric density of the food declines. A 25-year mission would require food that either lasts an order of magnitude longer than anything currently available or is produced aboard the spacecraft through agriculture. Bioregenerative life support systems, essentially onboard greenhouses, have been studied extensively but have never been demonstrated at the scale needed to feed a crew. Growing enough food for 4 to 6 people requires significant volume, lighting energy, water, and nutrient cycling infrastructure. The mass and power requirements of an onboard agricultural system capable of supplementing or replacing packaged food for decades add yet another layer to the already crushing mass budget. Now step outside the engineering constraints and consider what the crew actually experiences when they arrive. After 12 to 17 years of travel, enduring the communication delay, the isolation, the radiation, the confinement, the psychological strain, they reach Uranus orbit. What do they see? They see a pale blue-green disk hanging in darkness. Uranus is one of the most visually featureless planets in the solar system. Unlike Jupiter with its swirling bands and great red spot, unlike Saturn with its magnificent rings visible from millions of miles away, Uranus presents an almost uniform cyan sphere to the naked eye. Voyager 2's images from 1986 revealed a world so bland in appearance that mission scientists initially joked that the probe had photographed a billiard ball. Later enhanced images and subsequent observations by ground-based telescopes and the James Webb Space Telescope have revealed subtle banding, seasonal cloud patterns, and atmospheric dynamics. But to the unaided eye, Uranus remains visually underwhelming compared to the gas giants. The rings of Uranus exist but are thin, dark, and nearly invisible compared to Saturn's spectacular system. They would not provide the visual spectacle that a crew might hope for after a decade of staring at empty space. The moons, while scientifically fascinating, are small and distant. Even Miranda, the innermost of the major satellites, orbits at a distance of roughly 80,000 miles from the planet's center. To the crew, these moons would appear as tiny points of light, requiring telescopes to resolve into disks. The lighting conditions compound the sensory deprivation. At 19 astronomical units from the Sun, Uranus receives about 1/400th the sunlight that Earth receives. The illumination at Uranus is comparable to deep twilight on Earth, roughly 350 times dimmer than a bright sunny day. The planet and its moons are lit by a dim, distant sun that has shrunk from the life-giving disk visible from Earth to a bright but small point of light barely distinguishable from a very bright star. Shadows are faint. Colours are muted. The entire scene is cloaked in a permanent low-light gloom that no amount of spacecraft window design can overcome. The magnetic environment adds an invisible layer of hostility. Uranus possesses one of the strangest magnetic fields in the solar system. Unlike Earth, where the magnetic axis is roughly aligned with the rotational axis, Uranus's magnetic field is tilted approximately 59 degrees from its rotational axis and offset from the planet's center by about 1/3 of the planet's radius. This creates a magnetic field that wobbles chaotically as the planet rotates, producing a magnetosphere that is constantly reconfiguring itself. The radiation environment within this magnetosphere is poorly understood because Voyager 2's single flyby provided only a snapshot. A crew operating in Uranus orbit for months or years would be exposed to trapped radiation belts, whose intensity, distribution, and variability are largely unknown. The Casmius mission concept, presented at the 57th Lunar and Planetary Science Conference in 2026, specifically identified the magnetospheric environment of Uranus as one of the highest priority science targets precisely because it is so poorly characterized. This is telling. When scientists identify a phenomenon as a high-priority research question, they are acknowledging that current understanding is insufficient. For a robotic probe, insufficient understanding of the radiation environment is a risk factor to be managed through shielding and instrument hardening. For a human crew, it is a potentially lethal unknown. Operating in an environment whose radiation characteristics cannot be predicted with confidence means accepting a degree of risk that no crewed mission in history has ever accepted. Temperature at Uranus adds another layer. The upper atmosphere reaches a minimum temperature of roughly -224 degrees Celsius, making it the coldest planetary atmosphere in the solar system. colder even than Neptune despite being closer to the Sun. This extreme cold affects spacecraft operations in multiple ways. Thermal management becomes a primary engineering concern. Just 259. Electronics must be heated to function, mechanical joints must be protected from freezing, optical systems must be prevented from fogging or cracking. On a crewed spacecraft, the thermal control system must simultaneously reject waste heat from the habitat interior, where crew metabolism and equipment generate warmth, while preventing the exterior from reaching temperatures that would cause structural or mechanical failure. This bidirectional thermal management must function continuously for years with no maintenance from the ground. Even the orbital mechanics at Uranus work against a human mission. Uranus's extreme axial tilt of 97.77 degrees means the planet essentially rolls around the Sun on its side. During certain phases of its 84-year orbit, the poles point nearly directly at the Sun, creating extreme seasonal variations in illumination and atmospheric dynamics. The orientation of the ring plane and the orbital planes of the moons relative to an approaching spacecraft depend heavily on when the mission arrives. Certain arrival windows offer better geometry for moon flybys and orbital insertion than others, but these windows are separated by decades. Missing an optimal window could mean accepting a suboptimal orbit that limits scientific return or increases propellant consumption. The 2022 Planetary Science Decadal Survey recommended a launch window in the early 2030s specifically because a Jupiter gravity assist would be available, reducing transit time and fuel requirements for the robotic orbiter. That window was subsequently pushed to the mid to late 2030s due to plutonium production shortfalls. For a crewed mission, which would require even more precise trajectory optimization, the available launch windows would be even more constrained. Missing a window could delay the mission by a decade or more, during which political support, funding, crew readiness, and spacecraft systems would all degrade. Strip away the engineering details and look at what remains. A crew that has spent over a decade in transit arrives at a destination that cannot be landed on, that provides no usable resources, that generates almost no solar energy, that bathes them in poorly understood radiation, that presents visually as a dim, featureless disk in permanent twilight, that is surrounded by tiny icy moons offering no atmosphere and no shelter, and that sits so far from Earth that calling for help is a 5-hour exercise in futility. Mars is hard, but Mars gives you something back. It gives you ground to stand on. It gives you ice to melt. It gives you carbon dioxide to convert into fuel. It gives you a 24-hour day cycle to anchor your biology. It gives you a sky that changes, a horizon that recedes, a landscape that rewards exploration. Mars is a world that resists human presence, but does not reject it entirely. A crew on Mars can work outside, can build, can improvise, can adapt. Uranus gives you nothing. It takes everything you bring and offers only data in return. Data that a robotic spacecraft could collect almost as effectively, at a fraction of the cost, with none of the risk, and without requiring a crew to sacrifice decades of their lives to gather it. This is the devastating asymmetry at the heart of the Uranus question. The scientific value of exploring the ice giant is enormous and widely recognized. Understanding Uranus is critical to understanding the most common class of exoplanet in the galaxy. Characterizing its atmosphere, its interior structure, its magnetic field, and its moons would fill gaping holes in planetary science. The 2022 Decadal Survey ranked a Uranus mission as the highest priority flagship mission for precisely these reasons. But every one of those scientific objectives can be achieved by a robotic spacecraft. Not as quickly, not as flexibly, but adequately. The case for sending humans to Mars rests partly on science and partly on the unique capabilities that human presence brings to surface exploration. The case for sending humans to Uranus rests on nothing except the desire to say that we did it. And that desire, however deeply felt, does not justify asking a crew to spend a quarter century inside a metal tube, only to arrive at a planet that offers them absolutely nothing to work with. The destination is real. The science is real. The planet is there, spinning silently in the darkness, keeping its secrets behind veils of methane and hydrogen. But the gap between what Uranus offers to robots and what it offers to humans is a chasm so wide that no engineering brilliance can bridge it. The ice giant does not merely fail to welcome human visitors, it renders their presence meaningless in every practical sense. And it is this meaninglessness, this absence of reciprocity between the destination and the crew, that transforms the mission from a question of engineering into a question of ethics. Because the real horror of a crewed Uranus mission is not the engineering difficulty. It is not the communication delay, the propulsion burden, or the radiation exposure. The real horror is what happens to the human beings who go, what happens to their lives, their relationships, their sense of connection to the species they left behind. What happens when you send people so far from home, for so long, toward a destination that cannot sustain them, that the journey itself becomes the only thing the mission is? That is the threshold this story has been approaching, and it is time to cross it. There is a moment in every journey outward from home when the traveller looks back and realises that the distance has changed something, not just the view, not just the scale, something inside the experience of being a person connected to a place. Sailors in the age of exploration described this moment. Antarctic explorers documented it. Apollo astronauts spoke about it with an almost religious intensity. There is a point where home stops being a place you left and starts becoming a memory you carry, where the idea of return shifts from an expectation to a hope, and then from a hope to an abstraction. Every previous human mission to space has stayed safely on one side of that line. A crewed mission to Uranus would cross it. Consider what the mission actually looks like from the inside, not the engineering, not the propulsion budgets or the mass ratios or the delta V calculations. Consider the human life that unfolds within the mission's timeline. A crew is selected. For a mission of this magnitude, the selection process would begin a decade or more before launch. Candidates would be drawn from the most experienced astronaut corps in the world, people who have already demonstrated the psychological resilience, technical skill, and physical endurance required for long-duration spaceflight. They would undergo years of specialized training not only in spacecraft systems, orbital mechanics, and scientific instrumentation, but in medicine, surgery, dentistry, psychology, conflict resolution, mechanical repair, electrical engineering, agriculture, nuclear reactor operation, and 100 other disciplines that a crew 2 billion miles from Earth must master because there is no one else to call. The crew would train together for years before departure, forging the kind of interpersonal familiarity that either becomes deep trust or quiet resentment. There is no way to know which it will become until the mission is underway. Launch day arrives. The crew boards their vehicle, assembled in orbit over multiple launches, a habitat module connected to propulsion stages, fuel tanks, power systems, science platforms, and the accumulated supplies for a mission expected to last a quarter century or more. The final inspections are completed. The last supply vessel undocks and departs. The crew fires the transuranian injection burn, a sustained engine firing that accelerates the spacecraft out of Earth orbit and onto a trajectory toward the outer solar system. Within hours, Earth has shrunk from a blue marble to a blue dot. Within days, it is indistinguishable from the surrounding stars without optical magnification. Within weeks, even through the spacecraft's telescopes, Earth is just another faint point of light in the constellation of inner planets clustered near the Sun. The first year passes. The crew settles into routine, exercise, system checks, science preparation, communication with Earth, already delayed by minutes that stretch into tens of minutes, then hours as the spacecraft climbs outward past Mars, past the asteroid belt, past Jupiter's orbit. The crew watches Jupiter grow from a bright star to a visible disk, then shrink again behind them as they continue outward. If the mission uses a Jupiter gravity assist, There is a period of intense activity as the spacecraft executes the flyby, gathering additional velocity from Jupiter's immense gravitational field. For a few weeks, the crew has a destination to focus on, a planet to photograph, a gravitational maneuver to monitor. Then Jupiter falls behind, and the long emptiness begins. Year 2, Year 3. The spacecraft is now beyond Saturn's orbit, deeper into the solar system than all but a handful of human-made objects have ever travelled. The sun is noticeably dimmer, no longer the blazing disk that dominates Earth's sky, but a brilliant point source that provides measurable warmth only to the most sensitive instruments. The crew's communication delay with Earth has stretched past 2 hours one way. Conversations with family have become exchanges of video letters, recorded monologues sent into the void with the knowledge that a reply will not arrive for nearly 5 hours. Birthdays are celebrated with messages from home that were recorded the previous day, delayed by the steadily widening gulf of space. Year 4, Year 5, Year 6. The routine has calcified. Every activity aboard the spacecraft is governed by schedules designed to maintain physical fitness, psychological stability, and operational readiness. The crew exercises for 2 hours daily to combat the bone density loss and muscle atrophy caused by prolonged exposure to microgravity or the partial artificial gravity provided by whatever rotational system the habitat employs. They maintain the life support systems, replacing filters, cleaning water recycler components, and monitoring atmospheric composition. They conduct scientific observations of the interplanetary medium, measuring solar wind properties, cosmic ray fluxes, and dust particle densities. They study, they read, they watch entertainment media loaded onto the ship's servers before departure, a library that grows no larger as the years pass. They talk to each other. They try not to talk to each other too much. The psychological literature calls this phase the monotony plateau. It is the period after initial adjustment and before arrival anticipation, when the mission offers the least novelty and the greatest risk of psychological degradation. On a Mars mission, this plateau lasts perhaps 4 to 6 months. On a Uranus mission, it lasts the better part of a decade. During these years, the crew ages. This is obvious in the abstract, but devastating in the specific. A crew member who departed Earth at age 35 is now 41. Their children, if they have them, have started school, learned to read, made friends, lost friends, developed personalities and interests and fears that the crew member knows about only through time-delayed video messages. A crew member's parents have grown older, possibly ill, possibly dead. News from Earth arrives with a delay that makes it feel less like information and more like archaeology. By year 6, the crew member has spent more consecutive time away from every person they love than any human being in history has ever spent away from anyone. And they are not even halfway to Uranus. Year 8. Year 9. Year 10. The spacecraft has been travelling for a decade. It has covered roughly 1 billion miles, but Uranus, depending on the trajectory, may still be hundreds of millions of miles away. The sun has shrunk further. Outside the spacecraft windows, the universe looks exactly the same as it did 2 years ago, 5 years ago, 8 years ago. The same stars, the same blackness, the same unchanging void. The human visual system evolved to extract information from a rich, dynamic environment, full of movement, colour, depth, and change. Inside a deep space habitat, the visual environment offers almost nothing. The walls are the same, the equipment is the same, the faces are the same, the view out the window is the same. For 10 years, the sensory environment aboard the spacecraft deserves particular attention because it represents a deprivation that no previous spaceflight crew has experienced at this duration. Aboard the International Space Station, astronauts look down at Earth every 90 minutes. They see continents, oceans, thunderstorms, city lights, auroras. The visual richness of low Earth orbit provides constant novelty and a powerful psychological anchor to the planet below. On a Mars transit, the crew can watch Mars growing brighter and larger as they approach, a visible marker of progress. On a Uranus transit, there is nothing. The destination is too faint to resolve with the naked eye for the first decade of travel. Earth has long since vanished into the background star field. The sun has dimmed to a point source indistinguishable in apparent brightness from a moderately bright star. The windows show the same unchanging void, month after month, year after year. The human visual system evolved to extract survival information from a dynamic environment, to notice movement, to detect change, to scan horizons. Inside the spacecraft, it has nothing to work with. The psychological cost of a decade of visual monotony at this scale has no research basis because no analogous situation has ever occurred in the history of human spaceflight. Somewhere around year 12, perhaps year 14, the crew begins to see Uranus, not with the naked eye at first, but through the spacecraft's telescopes. A faint blue-green dot growing incrementally brighter against the star field. For the first time in years, there is something new to look at, something to anticipate. The approach phase begins, and with it, a resurgence of purpose and activity. The crew prepares instruments, reviews orbital insertion procedures, runs simulations, checks and rechecks the propulsion systems that must perform flawlessly to capture them into Uranus orbit. The mood lifts. The destination they have been travelling toward for longer than many marriages last is finally becoming real. Orbit insertion succeeds. The engines fire for a carefully calculated duration, shedding velocity, and Uranus's gravity captures the spacecraft into a stable orbit. For the first time since leaving Earth, the crew is somewhere. They have arrived. They are in orbit around another planet. The elation is genuine and overwhelming and absolutely temporary, because now they are at Uranus. And Uranus, as we have already seen, offers nothing. No ground, no air, no resources, no warmth, no sunlight worth measuring. A featureless disk of pale cyan below them, illuminated by a sun so distant it has lost its authority. Tiny moons visible only as points of light. Rings so faint they require specialized instruments to photograph. A radiation environment that no one fully understands. Darkness in every direction except the dim smudge of the planet below and the scattered glitter of stars that have been their only companions for 14 years. The science begins. The crew deploys atmospheric probes, commands moon flyby maneuvers, collects magnetospheric data, maps the ring system, studies the atmospheric dynamics with instruments far more capable than Voyager 2, carried 4 decades ago. The data is extraordinary. Each discovery adds to the understanding of ice giant physics, magnetospheric science, and satellite geology. Papers will be written, textbooks will be revised. The crew is doing exactly what they came to do, but the science phase has a planned duration, perhaps 2 years, perhaps 3. Eventually the data collection is complete, the probes are expended, the instruments have surveyed every target on the observation plan, and then the crew faces the moment that has been waiting for them since before they launched. The moment they must fire their engines again, escape Uranus orbit, and begin the journey home. 12 to 17 years home. The crew member who left Earth at age 35 is now approximately 50. They have spent 15 years inside this spacecraft. They have aged from early adulthood into middle age without ever standing in an open field, breathing unprocessed air, feeling rain on their skin, or holding another human being who was not a member of their tiny crew. Their children are grown. Their parents may be dead. Their professional peers on Earth have had entire careers, risen through institutions, retired. Technological generations have turned over. The world they return to will not be the world they left, and they still have over a decade of travel ahead of them. This is the threshold. This is the line that no previous human mission has ever approached. Not the distance, not the engineering, not the hostile destination. The threshold is temporal. It is the point where the duration of the mission exceeds the duration of the life you left behind, where the mission does not interrupt your life but replaces it, where you do not take a leave of absence from your existence on Earth but abandon it entirely, spending the prime decades of your adult life inside a sealed container moving through a void, connected to home by nothing except radio signals that take hours to deliver and hours more to receive a response. Every astronaut who has ever flown to the International Space Station has returned to a life that was still recognizable. Their home was still there. Their family was still waiting. Their career had paused, not ended. The world had not fundamentally changed in 6 months or 12 months. The astronaut reintegrated, resumed, continued. A crew returning from Uranus would find no continuity to resume. 25 to 35 years will have passed. If they left in 2045, they would return sometime between 2070 and 2080. The political landscape would be unrecognizable. The technological landscape would be unrecognizable. Cultural references, social norms, communication styles, even language itself evolves measurably over 3 decades. The crew would return as living anachronisms, relics of an era that the rest of humanity had moved beyond. Their children would be in their 40s or 50s. Their grandchildren, if any existed, would know them only as a name in a history book and a face in decades-old photographs. The crew would not be returning home. They would be arriving at a place that shares a name with home but bears little resemblance to the world they remember. This temporal displacement has a psychological weight that the word homesickness does not begin to capture. Studies of prisoners released after long sentences document a phenomenon called institutionalization, where the individual has adapted so thoroughly to the confined environment that the outside world becomes threatening, disorienting, and overwhelming. Returning astronauts from 6-month space station missions report a milder version of this, describing the strange difficulty of readjusting to open spaces, unrestricted movement, and unscheduled time. For a crew returning after 3 decades, the readjustment would not be a discomfort. It would be a full psychological reconstruction, and this assumes they return at all. A 25-year mission provides 25 years of opportunities for failure. Every system aboard the spacecraft, from the primary propulsion engines to the water recycler filters to the nuclear power supply, must function for a duration that exceeds the operational lifetime of most commercial aircraft, most power plants, most bridges. Mechanical systems wear out. Seals degrade. Electronic components accumulate radiation damage. Software encounters edge cases that no testing program anticipated. On a 3-year Mars mission, the probability of a mission-critical failure is calculable and manageable through redundancy. On a 25-year mission, the cumulative probability of at least one critical failure approaches certainty. Not because any individual system is unreliable, but because time is the universal solvent that eventually degrades everything. A failure in the outbound cruise phase might be recoverable if spare parts exist, and the crew has the technical skill to perform repairs. A failure during the Uranus orbital phase might be recoverable if it does not involve the propulsion system. But a failure in the return cruise phase, years into the journey home, with spare parts inventories depleted by decades of consumption, with equipment that has been running continuously for 20 or more years, with a crew whose physical and psychological reserves have been drawn down to their lowest levels, such a failure would likely be terminal. Not because rescue is difficult, but because rescue is physically impossible. No spacecraft exists or could be launched from Earth in time to reach a crew stranded in the outer solar system. The distances are too vast, the travel times are too long. A distress signal from a failing spacecraft between Uranus and Saturn would take 2 or more hours to reach Earth. A rescue mission, even if one could be assembled instantly, would take a decade or more to reach the crew's position. The crew would be dead for years before help arrived. There is a temptation, when confronting the extremity of a Uranus mission, to reach for historical analogies. To say that this is no different in principle from what Magellan's crew faced when they sailed westward into an ocean no European had ever crossed, or what Shackleton's men endured when the Endurance was crushed by Antarctic ice and they were stranded on a frozen sea with no communication and no rescue for nearly 2 years. Or what the first Polynesian voyagers risked when they set out across the Pacific in open canoes, navigating by starlight toward islands they were not certain existed. These stories are invoked constantly in discussions of ambitious space exploration because they carry an emotional authority that engineering arguments do not. If those explorers could endure isolation, danger, and the possibility of never returning, surely a modern crew with advanced technology could endure a mission to Uranus. The analogy is seductive. It is also completely false, and understanding why it fails is essential to understanding what a Uranus mission actually represents. Begin with the most fundamental difference. Every historical explorer, no matter how remote their destination, lived within Earth's biosphere for the duration of their journey. Magellan's crew breathed air. They drank water that fell from the sky. They caught fish from the ocean. They felt wind on their faces and rain on their hands. When they were hungry, they could sometimes forage on unfamiliar shores. When they were thirsty, they could sometimes find freshwater streams. The physical environment was hostile, often brutally so, but it was fundamentally compatible with human life. A sailor who fell overboard could swim. A castaway on a desert island could build a shelter from available materials. The biosphere, however grudgingly, supported human existence. A crew aboard a Uranus-bound spacecraft inhabits a bubble of artificially sustained biology, moving through an environment of absolute and instantaneous lethality. The vacuum of space is not an ocean that might drown you if you are careless. It is an environment that kills you in approximately 15 seconds if your habitat is breached. There is no foraging. There is no fishing. There is no finding fresh water on an unfamiliar shore. Nothing outside the hull sustains them. The biosphere is not the planet they orbit or the space they traverse. The biosphere is the vessel itself, a closed system carrying every resource the crew will ever access, with no possibility of replenishment from any external source. If the vessel fails, the biosphere ends. Shackleton's men, stranded on the Antarctic ice for 22 months, survived by hunting seals and penguins, melting ice for water, and burning seal blubber for heat. Their situation was desperate, but the environment provided raw materials for survival. They adapted, improvised, and endured because the Antarctic, for all its hostility, is a place where biological organisms exist. Animals live there. Water exists in solid form. The air is breathable, if bitterly cold. A crew stranded in deep space between Saturn and Uranus with a failed propulsion system would have no seals to hunt, no ice to melt, no air to breathe that they did not bring with them. They would have the consumables remaining in their habitat and the time those consumables could sustain them. When the consumables ran out, they would die. There is no improvisation possible when the environment contains literally nothing that a human body can use. The communication dimension of the analogy fails equally. Shackleton was out of contact with the outside world for his entire stranding, but the reason was technological, not physical. Radio technology existed in 1915, but Shackleton's equipment lacked the range to reach the outside world from their location in the Weddell Sea. Had he possessed a radio transmitter, he could have called for help, and a rescue ship could have reached him within weeks or months. The problem was equipment, not distance. For a crew at Uranus, the problem is distance in the most absolute physical sense. Radio signals travel at the speed of light and cannot be made to travel faster. Even if the crew possesses the most powerful communication equipment ever built, their distress signal will not reach Earth for nearly 3 hours, and a rescue mission could not reach them for over a decade. Shackleton's isolation was technological and temporary. A Uranus crew's isolation is physical and fundamental. The Polynesian voyagers offer perhaps the closest emotional parallel. People who set out across an immense ocean toward a destination they had reason to believe existed, but could not confirm, knowing they might never return. But the Polynesians carried with them the skills and knowledge to sustain themselves wherever they landed. Their destination, if they reached it, would provide soil, fresh water, edible plants, fish, timber for shelter. The Polynesian model of exploration was one of potential settlement. Arrival meant the possibility of a new life. Arrival at Uranus means orbiting a planet you cannot touch, studying moons you cannot walk on, and then turning around to face another decade and a half of travel through the same void you just crossed. The deepest failure of every historical analogy is temporal. Magellan's circumnavigation took roughly 3 years. Shackleton's stranding lasted less than 2. The longest Polynesian voyages measured in weeks or months. Even the most extreme examples of human exploration, overwintering in the Arctic, multi-year whaling voyages, or the rare cases of castaways stranded for a decade, fall far short of the 25 to 35 years that a Uranus round trip would demand. No human being in the age of exploration spent the majority of their adult life on a single voyage. A Uranus crew member would. And unlike every historical explorer, the Uranus crew cannot quit. A dissatisfied sailor could desert at the next port. A mutinous crew could turn the ship around. These options were often impractical or suicidal, but they existed as psychological pressure valves that prevented the feeling of absolute entrapment. A crew in deep space has no port. There is no direction to march. The trajectory is ballistic, following a path determined by orbital mechanics, and deviating from it requires propellant budgeted to the last kilogram for essential maneuvers. The crew cannot turn around because turning around would consume fuel allocated for orbit insertion. They cannot slow down because every change in velocity has downstream consequences for the rest of the mission. They are passengers on a trajectory that was calculated before they launched and that will carry them forward regardless of whether they want to continue. This is the reality that no historical analogy captures. Not the danger. Danger is common to all exploration, not the isolation. Isolation has precedent, not even the possibility of death, which every explorer has faced. What has no precedent is the totality of commitment. The absolute, irrevocable, decades-long surrender of personal autonomy to a mission architecture that cannot be altered once it begins. No explorer in human history has ever faced a situation where the decision to depart was also irrevocably and without possibility of amendment. The decision about how they would spend the next 25 to 35 years of their life. That is new. That is what Uranus demands. And that is why every comparison to Magellan, Shackleton, or the Polynesian wayfinders ultimately collapses under the weight of the difference. This is what separates a Uranus mission from every other human spaceflight concept ever seriously considered. It is not the difficulty of getting there, it is the impossibility of rescue. On the Moon, rescue was theoretically possible within days. On the International Space Station, crew evacuation is available at all times through permanently docked Soyuz or Dragon capsules. On a Mars mission, abort scenarios exist for various mission phases, and even in the worst case, the crew is within 3 years of Earth. On a Uranus mission, from the moment of transuranian injection onward, the crew is beyond the reach of any rescue capability that human civilization possesses or is likely to possess within the foreseeable future. This means the crew departs Earth knowing with absolute certainty that if anything goes seriously wrong, they will die. Not might die. Not face an elevated risk of death. Will die. No one is coming. No one can come. The nearest human beings are years of travel time away. The crew's survival depends entirely on the reliability of machines that must work for longer than any comparable machines have ever worked, maintained by a handful of people who must remain physically healthy, mentally sharp, and emotionally stable for longer than any human beings have ever been required to remain so under comparable conditions. This knowledge changes the nature of the mission from its first moment. It transforms the crew from explorers into something else, something that does not have a clean word in the vocabulary of spaceflight. They are not colonists because they are not establishing a permanent settlement. They are not emigrants because they intend to return. They are not exiles because they chose to go. But they share with all of these categories the defining characteristic of people who have crossed a boundary beyond which the connection to home becomes more theoretical than real. The philosopher Hans Blumenberg wrote about the shipwreck as a metaphor for human existence, the idea that consciousness is a kind of vessel moving through an environment it was not designed for, always at risk of being overwhelmed by forces it cannot control. A crew aboard a Uranus-bound spacecraft would live inside this metaphor literally. Their vessel is the only barrier between their biology and the absolute hostility of deep space. If the vessel fails, they fail. If the vessel endures, they endure. There is no middle ground, no partial survival, no limping home on damaged systems the way a wounded ship might limp to the nearest port. And here is the part that transforms this from an engineering discussion into something deeper. The question is not whether humanity could theoretically build a spacecraft capable of reaching Uranus and returning. Given unlimited funding, unlimited time, and unlimited tolerance for risk, some version of the mission might be technically achievable within the next century. The question is whether any human being should be asked to undertake it, whether the scientific return justifies the human cost, whether the knowledge gained by having a human crew at Uranus rather than a robotic probe is worth decades of human lives spent in confinement, isolation, and mortal risk. The honest answer is that it is not. Not because the science is unimportant. The science is profoundly important. Understanding Uranus is critical to understanding the most common type of planet in the galaxy, characterizing its atmosphere, interior, magnetosphere, and moons would reshape planetary science, inform exoplanet research, and answer questions about solar system formation that have persisted for decades. But every one of these objectives can be achieved by robotic missions at a fraction of the cost, a fraction of the risk, and without asking human beings to sacrifice the central decades of their lives to gather data that a well-designed probe could collect nearly as well. The Uranus orbiter and probe, if it is eventually funded and launched, will make the same long journey to Uranus, enter orbit, deploy an atmospheric probe, conduct a multi-year survey of the planet and its moons, and transmit its findings back to Earth. It will do this without a single human heartbeat aboard, without a single calorie of food consumed, without a single hour of sleep lost to anxiety, without a single family separated for a generation. The probe does not need to come back. It does not carry the weight of return. And that is the final devastating clarity that Uranus forces upon us. The first humans to reach Uranus will not come back, not because physics absolutely forbids it under every conceivable future technology, but because the mission as a human experience is so profoundly lopsided, so weighted towards sacrifice and so empty of reciprocity that the return is not the triumphant second half of the journey. It is a theoretical appendix attached to a mission that has already consumed everything the crew had to give. The return does not restore what the mission took. It cannot give back the decades. It cannot reverse the aging. It cannot rebuild the relationships that dissolved across 2 billion miles of silence. The crew returns, if they return, not as heroes stepping onto a stage, but as strangers arriving at a place they no longer recognize, carrying data that could have been gathered by a machine. This is the threshold that Uranus represents. Not a wall in the engineering sense, though the engineering walls are formidable. A threshold in the human sense. The point where exploration stops being a temporary departure from ordinary life and becomes a permanent severance from it. The point where the word mission stops meaning a task with a beginning, a middle, and an end, and starts meaning something closer to a sentence. A commitment so total, so consuming, and so irreversible that it changes the identity of everyone who undertakes it. The solar system is not a ladder. It is a series of concentric boundaries, each one marking a different relationship between the explorer and the home they leave behind. The moon is close enough that you can watch Earth hanging in the sky, blue and bright and reachable, a 3-day journey away. Mars is far enough that Earth shrinks to a star, but close enough that you can still hold a delayed conversation, still receive news, still feel connected to the species you belong to. Jupiter is far enough that the connection begins to strain. Saturn is far enough that it starts to thin. Uranus is where it breaks. Not because communication becomes impossible. Radio waves still travel at the speed of light. Messages still arrive, hours late, but they arrive. Not because the return becomes physically impossible. Given enough fuel, enough mass, and enough engineering, a trajectory home exists. It breaks because the human organism, the biological and psychological entity that has to survive inside the spacecraft for the entire duration, is not built for this. We did not evolve to endure decades of confinement in a sealed habitat, separated from every natural environment that sustains our mental health, cut off from every social bond that gives our lives meaning, aging in a metal tube while the people we love grow old without us. We evolved on a planet with open skies, changing seasons, communities of hundreds and thousands, physical touch, sunlight on skin, the sound of wind and water and other voices. Every one of these things would be absent for the crew of a Uranus mission, not for months, but for the majority of their adult lives. The first humans to reach Uranus, if they ever exist, will not be explorers in the way that word has always been used. They will be something new, something the language of spaceflight does not yet have a word for. People who crossed a threshold that cannot be uncrossed. People who traded their lives on Earth for a destination that offered them nothing except the knowledge that they reached it. People who looked back toward a pale dot of sunlight and understood, with a clarity available only to those who have travelled far enough, that home was not behind them waiting. Home was something that happened a long time ago to people they used to be, in a world that had already moved on. The terrifying truth about Uranus is not that it is far away. Far away is a number. A number can be overcome with enough velocity and enough time. The terrifying truth is that a human mission there would not just cross space, it would cross a boundary in the human experience of exploration itself. The boundary where going out and coming back stop being two halves of the same story and become two separate stories told about two separate lives. The crew that departs is not the crew that returns. The world that launches them is not the world that receives them. The mission does not end where it began. It ends somewhere else entirely, in a future that neither the crew nor the world that sent them can predict, carrying wounds that no homecoming ceremony can heal. Uranus will be explored. The ice giant's secrets will be unlocked. Its atmosphere will be sampled, its moons will be mapped, its magnetic field will be modelled with precision, but the explorers will be made of metal and silicon, not flesh and bone. They will be probes and orbiters and landers, machines that do not age, do not grieve, do not lie awake in the darkness, wondering whether the people they love still remember their faces. The machines will go because they can go without losing anything. The humans will stay because going would cost them everything. And in that asymmetry lies the final answer to the title of this story. The first humans to reach Uranus will never come back. Not because the physics forbids it absolutely, but because the mission would take so much from them, so many years, so many connections, so much of the life that makes a person, that even if their bodies return to Earth, the people who left would already be gone.